Here we have a tall, slender column that's undergoing a load test. And when the column exceeds its critical load, the column can buckle in the center. This is a common form of failure for tall, slender columns. The model that we're going to use to analyze these types of failures is based on work done by Euler in 1757, where he analyzed a beam that had impending buckling and observed that it had a critical curve to it that we could analyze. If we take a look at that curve, it looks a bit like the work we've done with deflecting beams. In fact, if we turn it sideways, we might recognize some of the formulas. Here we're compressing the column with a load P at both ends. We'd like to analyze it here in the middle. We can call this X, and we'll call this axis Y. And if we make a cut here, we can analyze the forces at the cut. Here's the external load, P. And here's the internal reaction, P. And summing the forces in the X direction, we can see that they'd be the same magnitude. And they're offset by a distance Y, which that's creating a couple in this direction. Therefore, we're going to have an internal moment here of negative Py, where that's the force P and y is the distance away, and it's a negative moment because it's concave down. And recall then that m is EI y double prime, which we found to be equal to negative Py for that cut. If we divide through by EI and bring this to the left side, we get y double prime plus P over EI y is equal to 0. And we should recognize that as a second order ordinary linear differential equation. And that's one that solution is well known. It's sinusoidal in nature, which is a hint that this beam, as it begins to undergo buckling failure, is doing so in a sinusoidally shaped fashion. We know from differential equations the form of this solution in general will be y is equal to a sine of kx plus b cosine of kx. And we have some boundary conditions here. One boundary condition would be at x equal to 0, y is equal to 0. We're back here at the origin. We can't have any deflection. Cosine of 0 is 1. Sine of 0 is 0. Y is equal to 0. So we find, therefore, that b is equal to 0. We don't need that term. The second boundary condition is at the other end of the beam. At x equal to L, y is again equal to 0. And if we look at that solution, we can ask, when will a sine of kx be 0? And there's two solutions. A is equal to 0, in which case if a and b are both 0, that's a trivial solution. And the other solution would be if we plug in L here, KL, the sine function will be 0 if that's equal to pi, or if it's equal to 2 pi, or 3 pi, or n pi for that matter. There's a family of solutions here that work. So from here we can say then that K would have to equal n pi on L for our boundary condition to work. Now to determine K, we need to take two derivatives of this. So y prime would be a k to the cosine of kx and y double prime being negative a k squared sine of kx. And we can plug these values into our original equation and find out what's required for that solution to equal 0, as it does here. If we do that, we'll get negative a k squared sine of kx plus p on ei times y, which is a sine of kx, has to equal 0 for our solution to be valid. And we see that these equations will cancel out if k squared is equal to p on ei. So that becomes our criteria for this to work, that we need k squared to be p on ei. So we can take the square root of that and put that up to here. And we see that this is equal to the square root then of p on ei. And that p is called p critical. It's the load that's going to cause impending buckling failure in this column. So let's solve this for p critical by bringing the square to the other side. And we'll get p critical is n squared pi squared ei on L squared. And that is the critical buckling load for the beam. So here it shows our sinusoidal curve. So we know that this is y is equal to some a sine of k x, where x is in this direction, and y is in that direction. And the form of it, we're getting half of a sine curve out of that. Recall for a sine curve, it starts at 0, reaches a maximum, and goes into the negative territory. And that's at pi, and this would be at 2 pi. So we're seeing that portion of the curve here as it begins to collapse. And here's a steel column that's been overloaded, and we can see it beginning to bubble. And here's what it looks like in a reinforced concrete column. Now let's look at this n squared for a minute. For n equal to 1, p critical is pi squared ei on L. And the failure mode will look like this. It'll be half of a sine curve, where that's L of that column. If we look at an n equal to 2 type failure, p critical will be 4 pi squared ei, where we square n, on L. And what that tells us is that this mode of failure would look like that. Now, that value is 4 times P1. Over here, this would be P1, call this P2. So it's unlikely that you're going to reach this form of loading. Naturally, your beam is going to fail at 1/4 of this value. However, what if we were trying to reinforce this column because we knew it could potentially have problems here in the middle? We reinforced the column, it would be inducing it to have an n equal to 2 type failure, in which case it would buckle like that. Now, interestingly enough, we could say this top half looks just like my original beam model did. So for L on 2, P would be an n equal to 1 failure, and we would get pi squared ei on L on 2. And notice that that becomes 4 pi squared ei on L squared, which is the same as what we had up here. So this would be the same solution. You can treat it as an n equal to 2 failure, or use the modified length, often called length effective. And for length effective, we're looking to try to make that half of a sine curve. That's our length effective generally, to fulfill the design of our model equation. We could also look at an n equal to 3 failure, in which case P3 would be 9 pi squared EI on L squared, and that beam would have 3 deflection points, and it could happen if beam were being doubly supported to minimize deflection. However, if you call L effective L on 3 and use our original formula, there's our half of a sine curve. This is going to give us the same solution anyway. So you'll generally see the equation written without the n squared, with the understanding we're going to look for L effective to make the equation work under any circumstance that we might have. On the other hand, there's nothing wrong with leaving the n squared there, because we do understand what it means when we talk about an n equal to 1, n equal to 2, or an n equal to 3 failure mode. And it reminds us that restraining the motion at certain points will only go so far in minimizing buckling. Regarding L effective, our goal is to look for half of that sine wave. That becomes our model. So here we have a pin, which is the model that we used. We have a force applied at both ends, which would be P critical. And we're looking for that half of a sine curve, where the other half we don't see. And that's because we're using pi in our functions. If you recall, pi takes us this far, and then 2 pi takes us that far. So our prototype n equal to 1 failure, that becomes L effective. In the case of a fixed free, where the bottom of the beam is embedded into the ground or bolted down, we want to look for, again, the half of a sine curve. And if we look here, we're out at the maximum y. We'd have to go this far to get back to the y that we started at. So here, L effective be 2 times the actual L. Here we have a pin fixed, where again this is firmly bolted to the ground, let's say. And our goal is to look for the half of a sine curve. And we can see here that that half of a sine curve will be about there roughly, which looks by eye to be about 3/4 of the way. And we'll find that L effective is taken to be usually 0.7 of L. And here we have one that's fixed and fixed, so it's bolted at the bottom and at the top rigidly, like a cantilevered beam basically. And in effect that holds it with no slope where it exits here, if we recall our cantilevered beam work. So where do you see the half of a sine wave? And we can estimate it to be someplace about here. And if we look, that's about half of L, and L effective is taken to be 0.5 L. Here's a summary of our values, where we need to understand the end conditions to define L effective. Now we could also look for the critical stress that would cause this to buckle. And in that case, it would be P critical on the cross-sectional area, which would be n squared pi squared EI on L squared A. And note that we have an I over A in here, which it's okay to leave them in there, but we could also take them out and look at the radius of gyration, R sub G, which is defined as the square root of I over A. For example, if we had a rectangular beam of base B and height h, I would be 1/12 BH cubed, and the area would be BH, and take the square root of that, the b's drop out. One of the h's goes, making that a squared, and you get r sub g would be h over the square root of 12. And the radius gyration values are listed in tables, so it's not uncommon to use this. If we substitute that into here, we would get stress critical is n squared pi squared E rg over L squared, and this is now squared too. Bring the square root to here. And we could take this and bring it down underneath, so all the geometric terms are together. And if we do that, we'll get stress critical is n squared pi squared E on L over Rg squared. And this has a special name. It's called the Slenderness Ratio. And it's a ratio of length to radius of gyration. And the radius of gyration includes information about the moment of inertia I and the cross-sectional area. And we'll see that our tables often work with this slenderness ratio. And with that, we have our two formulas for finding the limiting load for a column. Taking a closer look at this critical stress, we can see that if we plot the stress versus the slenderness ratio, it forms an inverse square relationship with the L on R slenderness ratio, and as such, we get this hyperbolic shaped curve here, which goes off asymptotically in both directions. However, at some point, the yield stress of the material itself will kick in, and that will limit the design of the column as well. So theoretically, the Euler curve will come up and reach a certain point here, where we would then have to switch and use our standard stress normal as P over A and limit the design by the yield stress. However, all of this is quite idealized. If you look at a plot of actual critical stress values, here we can see that if we assume the yield stress linearly reaches out until it intersects with the Euler's curve, would lead to erroneous results in that there is always some imperfection or slight bending in the column, and it's going to cause it to buckle or fail before then. So the actual plot for this would be something along this line. And from that plot, we can break columns up into three types. Short columns, where the stress is P over A, they're going to get crushed rather than buckle. Intermediate columns, where both scenarios are likely. And then for long columns, which follow our buckling relationship here that we've defined, along with a safety factor to pull us back a little bit. Here's a family of curves done experimentally by the American Steel Institute. And we can see here where there's a slight amount of bow in the column before they load it, and the amount of bow will dramatically change the buckling stress allowance. And again, here's our sigma yield intersecting with the Euler curve out here. So we do need some correcting factors for this. Here's a curve that was put out by the American Institute of Steel Construction for the design of steel columns, and they've curve fitted it with a parabolic arc that intersects the Euler curve at 1/2 of the yield stress. Recall our theoretical model would have it reaching out like this. So this gives us a correction factor. And if we look down here, they're dividing the two models by C critical, and they define C critical squared as 2 pi squared E on stress yield. If you're below C critical, we should be using this relationship. And if we're above C critical, we should be using the Euler relationship here. Keep in mind, they also recommend a safety factor down here. So they say that stress allowable will be stress critical on 1.92. So it's also including a safety factor to account for these irregularities. I should also point out down here, they state that your L on R ratio should never exceed 200. That column is going to be just far too tall. If you're working with aluminum, the Aluminum Associates Incorporated has also set out some guidelines, and it's driven by the types of alloys of aluminum that you might be working with. And they define an L on R ratio of less than 66. This would be the allowable. And for slenderness ratios greater than that, there's an alternate equation, and so forth. So again, trying to match the Euler curve down in this stretch with a linear function for a short column. If you're working with wood columns, the American Forest and Paper Association has put out a set of guidelines where they've been able to model our Euler curve with one equation, which includes the yielding portion. When using this, they assume you're building from some rectangular column with dimensions B and D, where D is the smaller of the dimensions, and rather than plotting a slenderness ratio on this axis, they actually plot L over D. So you have to be aware that they're using a different value on the axis. From there, they say the stress allowable is the adjusted stress times a constant, and then they give us the formula to find the constant P, which is quite an impressive formula, although if you put it into Excel, it's easy enough to generate on a regular basis. They also down here state that you should not exceed an L on D ratio of 50, or the column is going to be too tall, and they won't be permitted. So based on the material you're working with, there are guidelines out there for adjusting our curve from our hypothetical solutions based on idealized conditions to the real-world conditions. Recall when we first developed the model for buckling, we said that the offset load P generated an internal moment equal to negative P y. Well, if this load is moved and becomes an offset load, which we've seen in the past can cause large increases in stress, where now if we offset the load from the neutral axis by a distance of E, our moment will be minus P y plus E, that additional distance. And recall that that's equal to EI y double prime. So if we rearrange this, we'll find now our differential equation is y double prime plus PE on EI y is equal to negative PE on EI. So we still have our sign portion of the solution, but we also have a second non-homogeneous part that's going to generate a particular solution. And if we work this through, we'll end up with what we call the secant formula for beams under buckling with an offset load. Here's the family of equations that can be used to solve an eccentric off-axis load in a column. These two equations right here constitute the secant formula, and they'll work well for solving offset loaded beams when you know the value for P. However, if you're looking for the value for P, it's very difficult to extract it because it's buried in two places, and it will generally have to be done using a trial and error method. Fortunately, plots have been made using the secant formula that will allow us to compute the value for P for specific materials. In this case, we're doing this for steel, where here you'll see listed the yield stress and the E value for steel. Along the bottom, we have our slenderness ratio. And on this side, we have the stress generated, and it's plotted versus an EC on R squared term, where R is the radius of gyration. And we can do is look up the EC on R value and trace it across to the L on R slenderness ratio. And from there we'll know the yielding stress without having to solve it through the secant formula. Here we have a column made from a W12 by 50 structural steel I-beam. We're asked to determine the allowable load if it has an effective height of 24 feet. First, we can start by looking up the table values for a W12 by 50 I-beam, where the 12 designates its depth and the 50 represents its weight per foot, and we find it to be right here. So for our data, we have a W12 by 50. So it has a depth of 12.2 inches. And it has a base of 8.08. inches. And we're given the area here as 14.6 inches squared. And over here, there's two table values for the I, the S, and the R. And one of them is larger than the other. We can see that here. And what that represents is the two different axes here. So we have this neutral axis, which is 1, and the vertical neutral axis, which is 2. So we need to use the smaller numbers. If it were to buckle, it's going to buckle in the weakest direction. So this is the area moment of inertia. That's the section modulus, and that's the radius of gyration that we need. So we'll list all of these out. We won't need S in this case. So we have an I of 56.3 inches to the fourth, and we have an R sub G of 1.96 inches. We're told the length here is 24 feet, so the length effective is 24 feet. And be careful with the units. We want them all to be compatible. So that's 288 inches. And from there we can calculate our L on R ratio, the slenderness ratio. It'll be 288 over 1.96, which will be 147. If we look at the AISC guidelines for steel construction, we see that we should calculate the C critical value, and we need to compare it to our L on R ratio. So C critical squared is 2 pi squared. E in this case is 29 times 10 to the 6 divided by the yield stress of 29 KSI, which gives us a C critical of 126, and we have an L on R ratio 147. So our L on R is greater than C sub R, so that represents this as being a long column, and we need to use this regime over here, which is Euler's regime. So we'll be able to calculate the stress and the critical using Euler's function, but the AISC says we have to use a safety factor of 1.92 when we're doing that calculation. So for an L on R that's greater than C critical, we can calculate the Euler value. So P critical, pi squared EI on length effective squared, which will be pi squared. E is 29 times 10 to the 6. Our I value from the table is 56.3. Divided by length effective, 288 inches squared. and we get 194 kips from that. We could also calculate the critical stress as P critical on A, 194 kips, and the area we found from the tables to be 14.6 inches squared. We'll get 13.3 KSI. And we can compare that to stress normal, which is P over A. However, we know that this is a long column, and it's unlikely that that's going to be a problem. But if we look, the stress allowable is 29 KSI, and we're down around half of that, so that's not a problem. Now we have to apply our safety factor. And for long columns, the safety factor is a constant 1.92 value based on the AISC values. So stress allowable be stress critical on 1.92, which is going to be 6.9 KSIs, which is even lower than that value, so we're definitely not having any problems with yielding this. And we could also do P allowable as P critical on the safety factor. And we'll get 101 kips as the allowable load. Thanks for watching.